Hello everyone, my name is Yimin Lin. Today I'm going to present the work Efficient Entity Resolution on Heterogeneous Records. Entity resolution (ER) is the process of identifying and merging records that refer to the same real-world entity, which is a crucial step for both data cleaning and data integration. Due to the success of social and semantic web applications, a large and quickly growing volume of heterogeneous datasets has become available on the web. Here we address two motivations for ER on heterogeneous datasets. To find value from such data, one way is to analyze heterogeneous records directly. The other is to integrate heterogeneous data under a unified interface and then make data analysis on it. On one hand, many applications require us to analyze data directly under heterogeneous settings. For example, although users might be the same individuals in various platforms, their profiles and behaviors could differ greatly. For the product recommendations, it can be improved if more accurate and complete user behaviors are captured, which benefits from entity resolution to distinguish user behaviors under different platforms. On the other hand, another fashion to leverage such data falls in the scope of data integration, that is, transforming those data under a media schema and provide a unified surface for users. However, in many scenarios, the lineage of such records comes from heterogeneous sources, and the schemas of which could vary from source to source. To convert such records under different schemas to those under a predefined schema, two steps are often required: schema matching and data exchange. In the conventional framework, schema matching and data exchange are performed to resolve semantic heterogeneity and transform records to those under a predefined schema. Even though such framework works for many scenarios, it would lose information in some cases, which is useful or even crucial to entity resolution. Information loss arises from the difference of information content in target schema and source schema, which would bring about both false positive and false negative. Next, we use an example in the first picture to illustrate it. Consider a company with three types of customer records, each of which owns schema respectively. Given a target schema, name, position, address, city, and the schema matchings, we execute data exchange to convert the instance from source schema to target schema. Note that the ground truth is not required for our approach, but only for illustration. Now, considering records under the target schema. The similarity between records R7 and R8 is high under whatever similarity metric, such as edit distance, Jacquard similarity, and so on. However, they do not refer to the same entity. It's infeasible to correct this false positive in target schema. Instead, if we explore information from records from source schema, we found that R7 is the joint result of R2 and R4. Similarly, R8 is the joint result of R3 and R5. The information used for entity resolution, email, tel, contact number, and com type are dropped during schema matching. Based on this distinguished information, we could infer that R7 and R8 refer to different entities. Next, consider false negative error. In the example, we can see R7 and R9, they share few similar fields on the target schema, but they refer to the same entity. As we observe the records on the source schema, R9 is the joint result of R1 and R6. For R7 and R9, we examine the email and the tail, which is identical, and their com type is very similar. Thus, it's possible to draw the conclusion that they refer to the same entity. Based on this example, we describe the challenge for heterogeneous entity resolution as the following two aspects. First, we call it description difference. Two records referring to the same real-world entity may share few attributes, leading to low similarity, since they describe different aspects of one entity. As an example, consider R1 and R2. Ground truth indicates that refer to the same entity, but they only share one attribute, which is name, and the other 6 attributes are different. Thus, their similarity is low. The second challenge is, when comparing two records, lack of schema matching between source schemas may make similarity computation difficult. For example, for R1 and R4, since we do not know whether or not customer customer1.email and customer3.work mailbox refer to the same attribute, it's hard to compare corresponding attribute values directly. We capture this challenge as heterogeneous schema. Now, we are going to overview our solution for entity resolution on heterogeneous records. Due to description difference arising from heterogeneous settings, those records could hardly be detected by batch processing, and we propose merge and compare mechanism to handle description difference. That is, we merge any similar records into a super records, as shown in the third picture, the data structure. When deciding whether or not two records Ri and Rj are similar, instead of computing their record similarity straightforwardly, we consider the similarity of their corresponding super records. If their super records are similar, we deem that Ri and Rj refer to the same entity. Then we merge their corresponding super records to find potential new matches in later rounds. To facilitate the above process, we adopt an iterative method to find and merge similar records. The stop condition is that the similarity of any two super records is below a predefined threshold. In each iteration, we first generate candidate record pairs and then verify them. These two steps are introduced as candidate generation and verification as shown in the overview. Now, we will describe our algorithm, which is called HERA, Heterogeneous Entity Resolution Algorithm. The first step is basically candidate generation. This step proves these similar record pairs and ensures high similar record pairs as the candidates. If two records are similar, they must share some similar values. With this consideration, we aim to obtain the record pairs with at least one shared value. And to achieve this goal, we index similar value pairs such that a set of record pairs sharing at least one similar value could be obtained as the candidate set within linear time. Then, to refine candidate set for each candidate record pair, we derive an upper bound and a lower bound of record similarity with logarithmic steps. The second step is verification. For each candidate record pair, We aim to verify it by judging whether or not its similarity exceeds the threshold. The core of this step is to compute the similarity of two heterogeneous super-records. Such similarity computation is non-trivial due to the following two aspects. Schema matchings between two records are missing, and the efficiency need to be taken into consideration owing to the complex structure of super records. And for this, we propose two methods. One is instance-based method, and the other is schema-based method. The core part of record similarity computation is to determine the field matching set. And the goal of instance-based method is trying to find all similar field pairs. This operation can be transformed to performing similarity join on two value sets of a record pair, which can be faceted efficiently by the index. Then we model the problem of deciding field matching set as finding a maximum weight matching in bipartite graph. The second method is a schema-based method. Among predictions provided by the instance-based method, one attribute may match multiple attributes, but there's only one which is true. The determination of the matching relationship for such one-to-many matching is converted to the problem of finding the proper matching attribute from multiple choices. We propose a probabilistic method based on the majority vote, which can estimate the matching attribute with the upper bound of error probability. Finally, we will show the result of the evaluation. So for the dataset, we use D-Movies, which is a collection of movies sharing among IMDb and DBpedia. And we further extracted the two datasets DM small and DM large from the original dataset. And in the experiments, we use the following three techniques to do the comparisons. The first one is association, and the second one is correlation clustering. The third one is collective entity resolution. And then we can see there are 6 pictures below. The first 3 is about the precision recall and F measure on large datasets, and the last 3 pictures is the precision recall and F measure on small datasets. The conclusion is Hera can collect sufficient information in heterogeneous sources to improve entity resolution on homogeneous datasets, and it can overperform the state of art. Second is about the efficiency aspect. The results shows that leveraging index will reduce the number of candidate pairs very effectively. Thank you.